Section 7.6, precipitation reactions. So we gave an example of these. Sodium carbonate, which is present in laundry detergent, reacts with the magnesium ions and the calcium ions that are present in hard water. And it forms a solid, well, two different solids that precipitate out of solution and keep those ions from making scum with the soap in the detergent. These are examples of precipitation reactions. So when we say precipitation reaction, it's a reaction that forms a solid. The solid is called a precipitate. A little bit like meteorology, what is precipitation? It's something falling from the sky, right? Could be rain, could be hail, could be sleet, could be snow. Precipitation. And when we've done these in lab, when you mix two clear liquids, it looks like it's snowing, sort of, okay? A solid forms. That's a precipitation reaction. Here's an example. Potassium iodide mixing with lead nitrate. So here we have potassium iodide. That's a soluble compound. Lead nitrate is a soluble compound. Here's one of them. I guess that's the Ki. That's soluble. It looks like water. The lead nitrate is soluble. It looks like water, even though it isn't. Not everything that looks like water is water. When we mix these two together, we get this bright yellow solid forming. This is a precipitate, a solid forming. It's a precipitation reaction. Sometimes when you mix two aqueous solutions, you do not get a precipitate. You don't get one every time you mix two things. If we mix potassium iodide with sodium chloride, nothing happens. They just mix. Here's the potassium iodide and the sodium chloride, and then nothing happens. Okay, one of the evidences for a chemical reaction is the formation of a solid. There's no solid that forms here. There's no reaction. And so when we're writing the balanced chemical equation, we get off easy because we can just write no reaction, or you can even shorten that to NR for no reaction. So we need to learn how to predict the products of precipitation reactions and write equations for them. So important to understand that only insoluble compounds form precipitates. Only insoluble compounds form precipitates. So what we have to do is we have to look at the possible products and determine, is either of those an insoluble compound? When we made the lead iodide, if we look that up in the chart, it's insoluble. And so we can predict that that's going to precipitate. So let's look at that more closely. So here's the potassium iodide in a beaker. This is an illustration of what the ions are doing. Here we have the iodide ions and the potassium ions. This is a strong electrolyte. It dissociates into ions. So this couple went to the party and they're mingling. They're not hanging around together. They're just, mingling and meeting other people and stuff. They're going around the party. And then over here, we have lead ions and nitrate ions. And this is a soluble compound. And so it dissolves into ions as well. The nitrate ion, being a polyatomic ion, stays together as a nitrate ion. But it is separate from the lead. Okay? So we've got these separated ions. When we mix these, here's an illustration immediately after mixing. So now these two parties combine, I guess you could think of it that way. And so now we have all of these ions mingling together. So if people are going to pair up, if these ions are going to pair up, what are the possible combinations? Well, we could make a table to look at that. So we have two different cations. We have potassium ions and we have lead ions. And we have two different anions. We have I- and we have NO3-. So, the cations are like the guys and the anions are the girls. So the possible combinations are we could have potassium with iodide, or we could have potassium with nitrate. We could have lead with iodide, or we could have lead with the nitrate. Those are the possible combinations. 4 different ions, because they have to pair up positive, negative, there's only 4 combinations. So if we look at those combinations, 2 of them are the reactants. 2 of them are what we started with. Potassium iodide, that was one of the reactants. That one's soluble. Even if we don't go look it up on the table, we can tell because that was in the beaker. It dissolved by itself. It was fine. And then the lead nitrate is the other reactant. Those cannot be a precipitate. They were soluble. So our possible precipitates are going to be potassium nitrate or lead iodide, the other 2. So potassium and iodide went to the party together, and they like each other, but they're not going to go make a precipitate on the back porch, okay? They're not going to go make out for the rest of the party in the back because they don't like each other that much, okay? They're like, well, yeah, I could stand to ride in the car with you on the way to this party. I'd rather not go by myself. And lead and nitrate came together, but they don't like each other that much either. And so then we have to decide, is it lead and iodide that got stuck on each other, or is it potassium and nitrate? How do we know? We look it up in the table. Which of these 2 is insoluble? Well, if we look up potassium and nitrate ions, we find that potassium compounds are always soluble and nitrate compounds are always soluble. Potassium and nitrate are going to stay mingling and circulating in the party. They're not going to precipitate. If we look up lead iodide, we see that iodide compounds are generally soluble except for lead. And so that's our precipitate. It's this guy right here, the lead iodide. Whoops, skipped one. So here's an illustration of what's happening after this has mixed. The previous picture was instantaneously right after mixing. That was before lead and iodide had a chance to meet each other. But as soon as they meet each other, they precipitate and end up on the back porch. They're not circulating anymore. The potassium and the nitrate haven't met anybody they're that crazy about, and so they stay at the party and they're just, having fun. Okay? So we look at the possible combinations of the ions and we look up their solubilities, and that's how we predict what the precipitate is. Any questions? So here are instructions for writing equations. So some people find, a list of instructions very helpful, and others don't. So if you find them helpful, great. First thing is to write the formulas of the 2 compounds being mixed as reactants. And below that, you need to write the formulas of the ions. You need the formulas of the ions with their charges in order to be able to predict the products. Then we're going to swap anions and rewrite those ion formulas on the reaction side. And then we'll use the solubility rules to determine if either of those new pairs is insoluble. If they're both soluble, then we just write no reaction, or NR, next to the arrow because there's no reaction. If one or both of those is insoluble, then we have to write the formulas of the compounds. We use AQ to indicate the soluble product and S to indicate an insoluble product, S for solid. Then you have to balance the equation using coefficients. Remember, do not change any subscripts. Okay, you can't change the subscripts to balance the equation. So let's do some examples. Write an equation for the precipitation reaction that occurs, if any, when solutions of potassium hydroxide and nickel 2 bromide are mixed. So this is a more difficult problem because it gives you the names of the reactants instead of their formulas. So the first thing we have to do is figure out what the formulas for the reactants are. And so in these examples, we're actually doing, I think it was step 2, before we do step 1, because in order to write the reactant formulas, we need to know what their ions are. So potassium hydroxide. Well, potassium ion is K plus, and hydroxide ion is OH minus. Okay, and that's chapter 5. And if you haven't worked out chapter 5 yet, you need to get on it because it's just going to come back and bite you. So positive, negative, there was one of each is all we need. So KOH. And it says that these are solutions so that we know these are aqueous. So we're going to put AQ after that. So we're going to mix that with nickel 2 bromide. Nickel 2 is Ni 2 plus. Ni 2 plus. Bromide is Br minus. We have a plus 2 and a minus 1. We can do the crisscross thing and end up with NiBr2. And that's also aqueous. I left a little blank here in case I need to put a prefix, not a prefix, a coefficient in there. And then here's our arrow sign. On an exam, I'll be kind and I'll give you the formulas for the reactants. And so then you need to take them apart and write those ion formulas with charges below. Because what we're going to do now is we're going to predict the products. Potassium and hydroxide came in together. They were soluble. You know, they're just friends. And nickel and bromide are just friends. So we need to find out, are these other two combinations, are they going to really have some chemistry between them or not? Right? Yeah, bad jokes. Bad jokes. Those are the best kind. So we're going to swap the partners. We're going to try out potassium with bromide and nickel with hydroxide. And it doesn't matter which one you write as the first product and which you write as the second product. Because 1 plus 2 is 3, and 2 plus 1 is also 3. The order doesn't matter. It does matter that you put the cation first and then the anion, because that's how we always do it. It's Mr. and Mrs. just by convention. So we're going to swap these over here. So I'm going to put K plus with Br minus, and I'm going to put the Ni2 plus with the OH minus. And then there's a couple ways you could approach this. You could write the formulas for the compounds, or you could check out to see if they're soluble first. It might save you a little work. So if we go to that chart, which I'm not going to go back to because I'll lose all my writing, and we look up potassium, we see that potassium compounds are always soluble. There's no exceptions. So this guy, potassium and bromide, is going to be aqueous because that's a soluble compound. Then if we look at nickel and hydroxide, we see that hydroxide is in that group that's mostly insoluble. There are some exceptions. Nickel 2 is not one of them. So this one is going to form a solid. One of these is a solid, so then we have to finish out our equation. So I'm going to put the potassium and the bromide together, plus 1, minus 1, we just need one of each. So that's KBr. And we figured out that was soluble, so we'll put aqueous as the state symbol. And then nickel 2 plus and hydroxide is minus 1. So crisscross thing here, and we get NiOH2, and that's a solid. I need the parentheses around the hydroxide because that's a polyatomic ion. When you have more than one polyatomic ion, you put the shrink wrap parentheses around it and indicate how many of them on the outside. So I've predicted my products. Now I need to balance this equation. And we've learned how to do that. So I'm going to look at the left. I see I have 1 potassium, and on the right I have 1 potassium. So that's okay. We can balance these polyatomic ions as units, or you can balance the individual elements. So if I look at the hydroxide, I have 1 hydroxide ion on the left, I have 2 hydroxide ions on the right. So to balance the hydroxides, I need to put a 2 over here in front of KOH. I had already looked at potassium, and now I changed the potassium, so I need to fix that. I've got 2 potassiums on the left side, so I need to put a 2 over here. so that I can have 2 potassiums on the right side. See what I'm doing there? This is not the only way to balance this equation, but however you do it, you should end up with the same answer. Then I'm going to look for nickel. Nickel is, there's 1 on the left and there's 1 on the right, so that's okay. And bromine, there's 2 bromines on the left and 2 bromines on the right. And so this is balanced. If you find that your equation is impossible to balance, look at your compound formulas, because you probably did one incorrectly. Any questions? It's the balanced equation for this precipitation reaction. Let's do another one. Write an equation when solutions of ammonium chloride and iron 3 nitrate are mixed. So ammonium chloride. Ammonium is that funny polyatomic cation, NH4. And chloride is Cl-. We know that from the periodic table that it has a -1 charge. Iron 3 is Fe, 3+, and nitrate we memorize, and that's NO3-. And putting these together, for ammonium and chloride, we have +1, -1, and so we just need one of each, NH4, Cl. These reactants are solutions, so we don't need to bother looking them up. We can just put aqueous. Iron and nitrate, there's a +3 charge and a -1 charge, so we can do the crisscross thing here. We'll end up with Fe, NO3, 3. We need 3 of these guys to balance the +3 charge on the iron. And that's also aqueous. So the next step is to predict the products, and we do that by having these guys switch partners to see if they hit it off any better. So over here on the right, I'm going to write the ammonium and the nitrate. And I'm going to write the iron and the chloride. Now, if you put iron and chloride first and then ammonium and nitrate next, that is fine. So if we look up ammonium and nitrate in the table of solubilities, then we see that both of those ions form soluble compounds with no exceptions. So ammonium nitrate is going to be soluble. If we look up iron and chloride in the table, iron's not listed, but chloride is, and we look at chloride, there are some exceptions. Chlorides are mostly soluble. I think it's lead and silver. I think there's one other one, but not iron. Iron chloride is soluble. This is aqueous. If a solid compound doesn't form, if we don't have chemistry between one guy, one girl, so that they're going to go off and stick to each other, then nothing is happening. There's no reaction. So we're done. We just write N, R. No reaction. We always like to get these on a test because they're a lot faster. No balancing, no writing formulas for products. Any questions? So you swap the ions, and then you look at those 2 possible products to see if is at least one of them insoluble. If one's insoluble, then you have to finish it out. Here's another one. Solutions of potassium sulfate and strontium nitrate. What happens when we mix those? Okay, well, potassium is K+, and sulfate is SO4, 2-. So when those get together, we get K2SO4, and that must be aqueous because it's a solution. And then we have strontium. Strontium is Sr, And that's in group 2A in the periodic table, so we know it has a 2 plus charge. And nitrate we've seen before, and that's one we just memorized, NO3 minus. So plus 2 minus 1, do the crisscross thing, SR NO3 2, and we know that that's aqueous. Then we draw our arrow, and we swap partners. Okay, don't put potassium and strontium together. Those are two guys. Okay, this is not San Francisco. Okay, this is Central Valley. Okay, people are free to make their own choices, but this is think like 50 years ago. Would that have been acceptable at like a public party? No. Okay. So no judgments on people's choices here, but it just works for this illustration. So we put this guy with this girl and this guy with that girl, okay? And we see how much they like each other. So we're going to write them over here. We're going to put them next to each other. We've got potassium and nitrate, and we have strontium and sulfate. And then we go to the table and we look. Potassium compounds are always soluble. Nitrate compounds are always soluble. This one's aqueous. And then we look up strontium and sulfate. Sulfate compounds are generally soluble. See, now I'm blanking. I've got most of that table memorized. Except strontium? I was pretty sure. Okay, so sulfate compounds are generally soluble, but strontium is one of the exceptions. And so this is going to form a solid. Strontium and sulfate like each other a lot. Okay? They just really hit it off. So that's forming a solid. So now we have to finish this. Potassium is +1, nitrate's -1. So we just need one of each of those. And we determined from looking in the table that that's aqueous. And then over here, hopefully I've got enough room. We've got this is going to form a solid. +2 -2, so SO4. I'm writing it backwards, so I made sure it fit. It's not a very good S. Looks like some weird. Okay, just start over there. SRSO4. Solid. And then we have to balance it. On the left side, 2 potassiums. So I'm going to make there be 2 potassiums on the right by putting a 2 in front of the KNO3. I can't just change the subscripts. I can't just make it K2NO3 because potassium's +1, nitrate's -1, and they would not get together in that arrangement. I have 1 sulfate on the left side and I have 1 sulfate on the right side. I have 1 strontium on the left and 1 strontium on the right. I have 2 nitrates on the left and 2 nitrates on the right. So I'm good. These precipitation reactions are generally pretty simple to balance. So there's our balanced chemical equation. Any questions?